In the previous video, we say that we're going to convert digital to analog, right? And in order to do that, these are the points that we are given, alright? And we don't know how to solve this, right? Because we want to find the curve, but how do we find? We say that we want to use the difference method. And then, in order to connect this curve, I can connect in this interval, by this interval, alright? Which is somewhat reconstructing the signal itself. But this is not good enough, right? We say that it's not very easy. So therefore we actually propose using the zeroth whole order, or it's just some concept. You see? Just some concept of that, that's all. So it's some generalization of a certain concept. And these intervals between them is a period. I call this t, I call this 2t. These are the period, right? T is equals to 1 over f, right? And we represent this signal now as a certain rectangular system, okay? And if you were to increase the frequency over here, these intervals will become shorter, alright? And instead of this such a big chunk of stuff, our signal may be faster. If the frequency is faster, alright, this means we're gonna take in more sample points, alright, more digital points, because you're gonna sample more of the analog system, right? You're gonna take in more sample points, and more sample points means that you're gonna have more of this interval, less. The period itself is lesser. So instead of t and 2t over here, if I have a zoom in, alright, this is, for example, this is t, then this interval right here is simply 2t now. It's not this one anymore. This is the old system, right? If I increase the frequency, our 2t is different, my interval is different, 3t, 4t. So as you can see, that as my interval becomes so short that I can actually take in a signal that is such of a point. You see, it's much more better than the orange color one, right? The orange color takes only a few points, alright, which cannot actually do with things. If I were to take this, we can actually create a better curve. In order to create a better curve, we say that we're going to use the difference method, Euler's difference method, and therefore this is it. This is the Euler's difference method. There is a forward rectangular. Rectangular means that we are dealing things in terms of rectangular. This is the shape of a rectangular. Alright, if you were to get the intervals shorter, you're still getting a rectangular. Alright, and it's a forward and a backward rectangular. So the forward is simply sampling one of this point and this point. So you are going in the forward direction. If you are sampling from this point to this point, then you're going in the backward direction. So it depends on whether you're going in this direction or you're going in this direction, that's all. Alright, it's just simply the Euler's rectangular forward and backward method. More visual way is that a forward rectangular method is simply you're taking the calculation going in this direction, while the backward rectangular method is you're calculating from the backward direction. I should have connect all the points, alright, something like that. And we're calculating with the backwards direction. That's all. Okay. The reason behind why forward and backward, why do we use them? I think it's because maybe if you have information on the backward, then you use the backward. If you have information on the forward, then you use the forward. I don't know. Anyway, this is something I really don't know. Oh, in order to convey what is the meaning of this thing, alright, let me just write it down. This is if you still remember, this is the certain function at this particular point. Alright, this interval I call it 2t, I call this interval t, and I call this interval 3t, etc. Alright, 4t. Alright. So at this point of time, this function that describes this point is x 2t. And then at this point of time, this little point over here, I call this function xt. So this function describes this point. This function describes this point. Alright, x2t is simply this one, xk plus 1. Alright, and xt is simply this one. Alright, where the k itself is somewhat the time step, I would say. But okay, not the time step, sorry, my fault. The k itself is some initial value. Alright, what I mean, k is simply this k over here. This k will fit into a certain transfer function ks. Alright, and if you fit this number in, alright, then you're gonna give some curvature like this. Alright, in order to construct this curvature, this k value will be subbed into certain function. So if k is 2, for example, then 2 squared plus 2 is equals to 6. So x equals to 6 is this point. So this is x equals to 6. Alright, and then the next round it goes, alright, if k increases, maybe 4 now, then instead of 2 now, this is 4, then 4 squared plus 2 will have the next value of 18. So at this point, x is equals to 18. And from here, then I can minus away this one, and then I calculate the difference between them. Then I can construct a curve to fit back to our system already. Something like that. And therefore, I would believe that you already understand this one and this meaning of that. And that t is simply the time step. Alright, it's simply this time step. If you decrease the time step, like maybe it's instead of 2t over here, you talk about here, then this means that you're gonna have a more accurate answer. Alright, but sometimes approximately big time step, alright, will be good enough for some, because some signals may be too easy to construct. So using a larger time step is alright. And therefore this is something like approximate, and therefore this is an approximate sign. Alright, so the changes within the changes that describe this curvature can be used by this thing, by this formula itself. Alright, so this changes is only changing describing a changes between these 2 points only. Alright, and then the next 2 points you're gonna have another changes. So when you keep on subbing in, for example, if I sub in k and k1, this is x dot k. So there will be a new, for example, this is something like the Newton-Raphson method lah, okay? It's something like that, so I'll just keep subbing in the new k and things like that. Later on when you do an example, you know what I mean, but just take down, alright? So the backward system is working in the backward direction, it's going in this direction. So instead of k as this point, this is k, instead of k is at this point and k plus 1 is this point, now this is k and this point is called k minus 1, alright, which is this one. So the same thing applies for this thing itself. Okay, when you have a system, there is an error input into this transfer function and an output over here, I can simply write this phenomenon as the transfer function is equals to the output divided by the input error. Alright, and we from a certain source, right, for example k s plus a plus b, alright, this k is different from our this k. Alright, so please take note, and I'll denote this as k naught for better understanding. Okay, the differentiation from this k. Alright, so this k naught will differentiate from the k. They are totally two different things. Alright, it's not that I'll differentiate it, but I mean in terms of they are totally two different stuff. That's it. Okay, that's it. So we're actually interested in this point over here, u dot t. Alright, this is u dot t. Why this is u dot t, and why are we interested in this point is because we are interested in the calculation. Alright, u dot t is simply the next point. Alright, simply the next point, meaning we're talking about this new point over here. Alright, meaning this is the line that I've drawn using the first step of forward rectangular, and then I found this line. Using this line, I input another value of k, and then I just sort it out, and then I'll just plot it out in terms of this curvature over here. Alright, this kind of give me an understanding of certain stuff. Alright, in fact, just now I say that after I found this one, for example, if I sub in a certain value of k and this k, I have this value over here, and then this value I sub in over into the next stage, and then I run the same system again. I don't think so, I don't think so. Okay, I don't think this is it. I think when I sub in a certain k and a certain k, I mean k plus 1, alright, the output over here only gives us this line over here. Alright, and then we know that there is another k value when we feed back in again, and this k value will be this point and the other point over here. So they'll create another line using this equation, alright, or using this number, and then we repeat again and again, then we'll form another line. I think you're starting to get more confused, but anyway, but still, the purpose of finding u dot t is simply to find this difference over here. We are actually interested in finding this difference. So the first round, for example, if the first round I send a certain signal, alright, if you construct this line over here, alright, you construct this line over here. The second round I send, you construct the next line. Then the third round I send a feedback, you construct. The fourth round I send, you construct. So this line is simply the construction of this curve, and it's totally unrelated to subbing in back into this one and then going back and again and again. It's not doing that. It's taking new values based on how many feedback system you are going. So one feedback system will give you k, the first k, and then you just sub in the first k into here, and you find the first x dot k1, which is this line over here. Then next, you feedback in, you'll send you another k value, which is k2. So you just sub in k2 as inside here, you'll get x dot k2, which is this line, which is this curve. Next round, send you another one k3. Then you'll just sub in back again into this equation, you'll get another value for x dot k3, and this is another. In fact, this isn't a value, but rather than more on the. Yeah, this should be a value. But anyway, at least this is something to what I want to convey. Alright, for u dot t, it's simply just to construct this line over here. So we are actually interested in finding the u dot t itself. But anyway, let's continue first. If you know that u dot t is over here, then u should be somewhere over here, I think. Yes, correct, because it's us. But anyway, do you find this familiar? This is actually what we have done earlier previously. So in order to solve, I'll just rearrange things. So I'll just bring up s plus b to the numerator, and this one to the numerator of the other side. So why do I have things like this? Alright, and then I'll just expand it. I'll have sus plus bus. Alright, is equals to this. So I'm simply multiplying in, just expanding the terms only. Alright, I'm just simply multiplying es over here. K, I keep it constant outside. Okay, and if you remember, sus is simply u dot t. Alright, I've proved to you. Alright, plus bus. Just a side note, if you forget, u dot t. Okay, for example, y dot t, it's Laplace transform. Alright, it becomes sys minus y0. If initial condition stating that y0 is equals to 0, then this thing will become 0, and therefore I have y dot t is equal to sys. So in this case, we are inverse Laplace transform. Alright, so sus is in fact this one. So inverse Laplace transform u dot t. So this is why this is over here. I hope this is at least a short understanding will do. At least you don't need to go back other stuff. Anyway, so bus is simply b, is still the same thing. Alright, it's just inverse Laplace transform for a differential equation. It's bu. Okay, same as this one. So ses is simply e dot t plus ae. Okay, should be ut lah, okay, to be more exact. So how does the Euler's formula comes in already? If you take a look at this, it's simply the representation of this one. Alright, and you come out into the time domain. Alright, once you inverse Laplace is always in the digital domain, I believe, and the time domain is simply in terms of going towards the analog system, digital to analog already. So in this case, u dot t we can represent in terms of the Euler's formula, which is this one. So I'll just copy it. Forward and backward is simply the same thing, but it depends on what situation where you really need it. So we just sub in u dot t, because this is simply u dot t and e dot t over here. So just simply subbing in u dot t as instead of x, alright, we just sub it as u. So uk plus 1 minus uk over t, the time period, and then the rest is the same. For the case of e dot t, instead of x, now we sub it as e. So I have ek plus 1 like this, and then plus aet. Okay, and this is how you apply the Euler's formula. Alright, this is the Euler's difference formula. So this is how you apply inside each of them. Okay, now when you have a first round of a input, meaning you have a first feedback system going in this direction, you have input a k1 over here. So this k1 will be subbed into this k, alright, this case. So in this case, for the u graph, you're starting to draw up a new graph like this, and maybe for e, you'll have something that goes on like this. And then the next round is going to send another k2 over. So then the next k2 value, alright, feedback value, will be subbed into this equation again. Alright, this equation again. And they will actually plotted out another new curve. And you'll plot another new curve. And so on. And you'll just plot out a certain curvature out already. So therefore u as the output, and then this is es, which is the input. As you can see, this is input into the system. Alright, so this is the input, and the relationship between them can be constructed by the rest of the stuff already. So as you can see, this is the somewhat, you can visualize things in a more easier way already. ut and et is simply your inputs. Alright, your inputs meaning that this is input es, right? Es is simply what? Es, if you're talking about time domain, is actually et. us in the time domain is actually ut. That's all. So when you actually draw the graph from here, maybe ut is something like that, and then et is something like that. Alright, so actually this can give you a very clear look of each of their own graph itself, and you can know how the changes has occurred within each of the system. This is the comparison between the input and its somewhat derivative. This is a comparison between its input, the output and its output derivative. Things like that, how things changes. So I hope that this is a very clear, good example for the applications and the conceptual understanding for Euler's forward. Perhaps same thing for backward. Rectangular meaning it's rectangular formula. And next video, an example to do it. See you there.